That orange ring at the base of a traffic cone isn't decorative. It's a precision-engineered counterweight, and without it, cones would blow off a highway at 55 miles per hour within minutes of being placed. Here's what you'll actually learn. Why cones tip over without ballast, how engineers calculated exactly how much weight to add, what happens when manufacturers get it wrong, and where the same counterweight logic shows up in objects you use every day. Most people assume traffic cones are just simple injection-molded plastic. Cheap, disposable, not particularly engineered. And to be fair, the visible part mostly is. The body of a standard 28-inch road cone is polyvinyl chloride, or a low-density polyethylene blend, and the whole cone above the base weighs somewhere between 1.5 and 2.5 pounds. It's light, flexible, UV resistant. Designed to survive being run over, spring back, and keep working. That flexibility is the whole point. A rigid cone would shatter under a truck tire and send shrapnel across a lane. But that same flexibility and light weight creates a serious aerodynamic problem the moment you set one next to a highway. Here's the physics. When a vehicle moves at highway speed, it drags a pressure wave, a wall of turbulent air. For a semi-truck at 65 miles per hour, that turbulent wake can generate a local wind gust on a roadside object of 50 to 80 miles per hour. A 2-pound cone sitting on asphalt has almost no friction grip. Its tapered, round body acts like a sail. It catches lateral wind loads and generates a tipping moment, a torque around its base. The question engineers have to answer is, how much downward force at the base cancels out that tipping torque before the cone goes horizontal? The steel ring answers that question. It's typically cast iron or steel, ring-shaped, sits flush into a molded recess in the rubber or PVC base, and on a standard 28-inch American highway cone, it weighs between 4 and 7 pounds. That's often more than twice the weight of the cone body itself. The weight is positioned as low and as wide as possible, which maximizes the lever arm working against the tipping moment. Basic statics. Restoring moment equals weight times horizontal distance from the tipping edge. A wide, heavy ring at the very bottom of the cone gives you the largest possible restoring moment for the least added material. Federal Highway Administration guidelines and the MUTCD, the Manual on Uniform Traffic Control Devices, require that cones used on roads with a speed limit above 45 mph meet specific wind resistance standards, and for many applications that means a cone with a base weight that keeps it upright in a 65 mph wind gust. The ballast ring is how manufacturers hit that spec reliably. Not every country does it exactly the same way. In the UK, traffic cones follow BS EN 13422, the European standard for temporary road equipment. British cones tend to have a broader, flatter base geometry rather than a tall, narrow profile, which lowers the center of gravity geometrically rather than purely through ballast weight. Some European manufacturers fill the base with a rubber compound poured in during molding rather than inserting a separate metal ring. The result is similar: low center of mass, high stability, but it changes the recycling and end-of-life story. A cone with a poured rubber base is harder to separate into material streams. The discrete metal ring in American-style cones can actually be removed, which matters when a cone body cracks, and the expensive steel insert can be salvaged for a new shell. In high-volume road construction, where a contractor might deploy 10,000 cones, that reusability has real cost implications. The deeper reason the base weight matters is one most people miss. Cones aren't just passive markers. They're load-bearing elements in a traffic control system that has to work autonomously without anyone standing next to it. Once a cone is placed and the crew drives away, it has to hold position through every truck pass, every weather change, every hour of the night. The engineering term for this is passive reliability. A cue card taped to a lectern fails the moment there's a breeze. A cone with the right base weight keeps working at 3 a.m. on an interstate when no one is watching. The ballast ring is an investment in unattended performance. And because these objects exist at the edge of moving traffic, failure isn't just inconvenience. A cone that tips into a live lane at night is a genuine crash hazard. The steel ring is cheap insurance against that failure mode. That failure mode has happened at scale. During a road resurfacing project in Texas in the summer of 2019, a subcontractor used cones that met the minimum spec for roads under 45 mph deployed on a 70 mph highway. Sustained wind from passing trucks toppled dozens of cones over several hours during an overnight shift. Several cones migrated into the driving lane. No injuries occurred, but the incident triggered a review of cone procurement specifications for that contractor. The lesson was obvious in retrospect. Cone weight specs are tied to speed limits, and substituting cheaper lightweight cones to cut costs on a high-speed deployment is not a minor shortcut. The base weight category is the critical purchase decision, and it's the one that gets cut when someone's buying on price alone. The counterweight principle shows up in more places than you'd expect. Retractable banner stands, the kind at trade show booths, have a cast iron foot that keeps the base from tipping when someone walks by. Tall floor lamps use a weighted base for the same reason. Sailboat keels are the large-scale version, a torpedo-shaped lead bulb at the bottom of the hull that uses mass and lever arm geometry to counter the tipping force of the sail. Even a well-designed wine glass has its mass concentrated in the base rather than the bowl. Every slender, tall object that has to stay upright in a dynamic environment is solving the same equation. Traffic cones just happen to be one of the most utilitarian, unglamorous expressions of it. A piece of steel that costs less than $1, hidden inside a cone most people never think about twice, is doing continuous physics work every time a truck rolls past at highway speed. The cone is light, so it survives impact. The ring is heavy, so it survives wind. Those two requirements pulled in opposite directions, and the base weight ring is the compromise that makes the whole system function. Engineering is usually like that. The part you don't notice is the one doing the most work. If this is your kind of thing, the why behind the everyday. Object Theory drops new ones Monday, Wednesday, and Friday.